So today I'll be going to talk about spontaneously broken boosts in CFT. And this is a work done with Zohar, Mark, and Avia from Simon Center. And yeah, during the pandemic times, it has been a wonderful collaboration because it's mostly done over Zoom. And to begin, the basic idea is that whenever we have a spontaneously broken symmetry, there are some, as you all know, there are Goldstone bosons, and correspondingly there are some Goldstone theorems, and there has to be some states which, and these Goldstone theorems are theorems for infinite volume theory, and there has to be some states which saturates these Goldstone theorems, and this implies existence of some states in the infinite volume theory, and which also implies existence of some states in the finite volume theory for which we are taking the infinite volume limit. So the idea is to look at those Goldstone theorems in the infinite volume limit and put constraint on the spectrum of the theory living on the finite volume. So the aim of this talk is to unpack whatever I said in the following 1 hour. So let us begin with the very basic thing. What do we mean by Goldstone theorems in this context? So consider a d-dimensional QFT with a Poincare invariance, and also say there is some continuous internal symmetry with Q being the generator. So when we say there is a spontaneous symmetry breaking, what we mean that there is a state omega, and there is some order parameter O, such that if I take the commutator of this charge and the order parameter in this state omega, then this is non-zero. Now there are one point to remember, that this equation as it is cannot be satisfied in a finite volume, because in finite volume you can diagonalize the Q, and then of course if you can diagonalize the Q, then this commutator is forced to be 0. So spontaneous symmetry breaking is inherently an infinite volume phenomena. It can only happen in infinite volume. So what happens that in a finite volume theory you have a Hilbert space, and as you take the infinite volume limit, this Hilbert space becomes closer and closer to some direct sum of some sub-Hilbert spaces. And this sub-Hilbert space cannot talk with each other by action of local operators. And that's why in the infinite volume limit, we are forced to sit in one sector, and that's why the super selection sectors arise, and we have the notion of spontaneous symmetry breaking. So that's one aspect. And if that happens, then in the infinite volume limit, in the infinite volume theory, we have some equation like this, and this has implication in terms of correlators. What kind of implications? So this is what we'll dub as algebraic decay of correlator. For example, if you take the charge density J0 and take the order parameter O, then this correlator cannot decay faster than x to the power minus d minus 1. This is a direct implication of this equality, of this inequality, or the fact that it is non-zero. And if you further assume something about the matrix elements, then you can also show that the 2-point correlator of this order parameter cannot decay faster than x to the power minus d minus 2. And now you can see that because here d minus 2 appears, if you plug in d equals 2, that means it cannot decay. That means this correlator will not follow the cluster decomposition rule, which is the familiar phenomenon. We all know in d equals 2, any internal symmetry cannot be spontaneously broken. So this is the familiar Coleman-Marmon-Wagner theorem. So this is a reincarnation of that theorem. Now, once we understand this setup, things get slightly different when we talk about space-time symmetries, the breaking of space-time symmetry. So, and because we ultimately will be going to talk about boost symmetry, so let us think about breaking of space-time symmetry. So again, the setup is a d-dimensional QFT with a Poincare invariance. So, and we have a conserved stress energy or EM tensor, so which we call T mu nu. And using the Killing vector of the space-time, we can construct the currents which are conserved. Now, again, by when you say breaking, we basically take this charge and find an order parameter so that the commutator of these two quantities evaluated in some specially chosen state is non-zero. So in particular, we will be looking at boost symmetry. So what is boost generator? Boost generator is basically the integral of this quantity here. Now, unlike the case for internal symmetry, here you will see that there is an explicit dependence of X. And if you do a naive scaling argument, then you will see that because of this presence of this quantity X here, the correlators of some component of stress energy tensor and and the order parameter O cannot decay faster than x to the power minus d, as opposed to x to the power minus d minus 1 in the internal symmetry case. So here we see that there's a 1 power of mismatch because of, and this is happening because of the presence of these explicit factors. So this means because this is 1 power down, this means basically that in d equals 2, for example, we can break boost symmetry. So there is no Coleman's theorem for boost symmetry breaking in the d equals 2. Later we will see that this indeed happens in 2D CFT. We can actually break boost in the sense of this equation. But nonetheless, the breaking of boost symmetry is conceptually very different in the following sense that so suppose you take theory on a finite volume. So you have a cylinder R times SD minus 1. So there you are inherently breaking the symmetry between time and space. So in some sense, there is no boost symmetry if you put the theory on a finite volume. So it only arises in the infinite volume limit. So while there is no boost symmetry in the compact space, but suppose you take this, so you're taking theory on a R times SD minus 1, so you have a spatial sphere. But if you look at a very small patch of the spatial sphere, you will see that there is an approximate boost symmetry because on that small patch, it looks like a flat thing. And this approximate boost symmetry can be spontaneously broken in the infinite, and looking at the small patch basically means you are taking infinite volume limit. So in that limit, this approximate boost symmetry can be broken. But since there is no boost symmetry in the compact space, so we cannot think of diagonalizing it. So there is no notion of superselection sectors, unlike the internal symmetry case. But even though there is no superselection sectors, I can still write down this kind of equations in the infinite volume limit. And this immediately implies some constraint on the correlators involving the stress energy tensor and this order parameter O. So there will be gapless excitations. And so the main point is the algebraic decay and the gapless excitations around this state, omega, in the infinite volume theory will imply some constraint on the finite volume theory. So even though there is no superselection sectors, we do have some algebraic decay, we do have this equation, and we do have this implication of these equations.
Can I ask you a question?
Yeah, sure.
Does this happen only for boosts?
That's a good question. I guess, yeah, I guess at least for the boost, the space and the time symmetry is broken. So, but if you think about the rotation, then of course the rotation symmetry is preserved on the sphere. So still you can think about these things.
Yeah, right. I was just thinking of the fact that it seems that it's crucial that the generator contains the X, but then maybe it's not.
Oh yeah. It's crucial that the generator. So the fact the generator contains X is important for this thing to happen. So because in the previous slide, there is a decay x to the power minus d. And the fact there is no super selection sector is related to the fact that there is no notion of boost symmetry in the compact space. Yep. Okay, very good. So as we said that this puts some constraint because this basic equation here. So what kind of constraint can we think of? So let us first give a very intuitive physical argument, and then we will go into more details. So suppose you take a theory and put it in a box of size L, and you also choose the energy so that also choose a state which has a finite energy density epsilon. So of course, in the infinite volume limit, your length scale would be epsilon to the power minus 1 over d. This is basically the scaling dimension analysis scaling argument. So basically you have two scales. One is epsilon to the power minus 1 over d, which is like the very small scale, which is the UV scale. And then there is a length L, which is the IR scale. And if you try to probe this theory on a length scale, which is much bigger than this one, but much smaller than this one, then there will be algebraic decay because because of the fact that finite energy density state will break the boost. So I have not yet told you how finite energy density state breaks the boost. I will come to that later, but for now, just believe me that finite energy density state breaks boost. And because, as I told you, that breaking of boost implies some algebraic decay, that means in this range, we will have some algebraic decay. Now, what does, now if we have a theory where on the length scale, in between these two length scale, we have an algebraic decay, what does it mean? It means that there has to be a gap, and that the gap should be smaller than this inverse length scale, which is epsilon to the power 1 over d. Because if the gap is not smaller than epsilon to the power 1 over d, then we'll not have a algebraic decay. Rather, we'll see it as a mass term, and there will be exponential decay. So the fact we have a power law decay immediately tells you that there has to be a gap which is smaller than this inverse of this length scale, which is the energy scale. So this tells you that it has, so you can parameterize it with this factor gamma, which is positive number. And then you can do the dimension analysis and immediately naively write down the gap scales as epsilon to the power 1 minus gamma over d times L to the power minus gamma. So basically this factor of L makes up for the dimension for the energy. So now the question is, what is the value of this gamma? So the most natural value motivated by the RG sense is 1, because if we assume if we flow to the deep infrared, we reach a fixed point of RG flow, and suppose there is a scale invariant field theory which describes this theory, then we would immediately tell that E gap has to scale as 1 over L, because that's the scale invariance. And then we will immediately conclude that gamma is 1. That's like a naively motivated, physically motivated an argument. Now you can take this whole setup, the whole physical argument I just told you, and ask what happens in a CFT. So of course you can put a CFT, you can put the CFT on a cylinder, so which is R times SD minus 1. So this setup. And in CFT, we know there are spectrum of primaries and descendants, which are characterized by the scaling dimension delta and some spin J. And by radial quantization, the energy is related to delta over R. And you can run the exactly same argument that I told you. And that immediately tells you that the energy gap of the CFT, if you put it on a finite volume, has to scale like epsilon to the power 1 minus gamma over d times R to the power minus gamma. So basically the capital L, the size of the box, gets replaced by the radius of the spatial sphere. And then you can, and again, you are thinking about a finite energy density state. So you can relate this finite energy density with some delta omega, some scaling dimension of some primary operator, which creates a state by radial quantization. And if you plug that back in and rewrite everything in terms of the inherently CFT quantities, you will see that the delta gap over this spatial state delta omega scales like delta omega to the power 1 minus gamma over d. So to summarize, you take a state delta omega so that you have a finite energy density, and then you take infinite volume limit, and you immediately see that above the state delta omega, there has to be a gap, and this gap should scale like delta omega to the some power, and this power is strictly less than, like, it has to be less than or equal to 1 over d. So I parameterize it as 1 minus gamma over d. So as I told you that so there is a constraint. So we write down this constraint in terms of CFT quantity, but you will immediately tell me that from a CFT perspective, this constraint is trivial for the following sense, because if you take a primary state which has a scaling dimension delta omega, then of course you can create this finite energy density state, but there will be descendants of this primary, which are of course in an order 1 gap in a delta variable. So this gap or this bound is easily satisfied by these descendants. But the twist in the story comes from the fact that as I will argue later, that for these Nambu-Goldstone-like theorems, these descendants don't really play any role. So they go out of the game, and the only players in the game are the primaries. So whatever constraints we'll have from these Nambu-Goldstone-like theorems is applicable for the primaries. And so that means we will have a bound for explicitly, we will have a bound on explicitly on the spectrum of primaries. And by this, then by this delta gap, we will mean the gap in the spectrum of primaries over the state delta omega. So in what follows, we will make these physical insights precise and argue for gamma equals 1. So this will be my next task. So is there any question at this point?
This is consistent with what we know, for example, in the O2 model, where the first primary over the lowest is at what, square root of 3 away. That gap is like square root of 3. That's it.
Yeah. So there the case is, so when gamma is 1, so the gap is of order 1. So it's of course satisfied by those Regge trajectories. Yeah.
Mm-hmm. Okay.
Because there we have an order 1 gap.
Mm-hmm. Mm-hmm.
So
sorry.
Yeah.
Sorry, I have a question. I mean, is it also true for the case Luca gave a talk about? I mean, when you have vortices, don't you have much smaller gap?
Just wait for probably 20 minutes.
Okay. Okay. I'm sorry. Okay. Yeah. Okay. Of course you know about that. Okay. Sorry.
Yeah, I'll come back to that. Yeah. Okay. So if not, to put things on the bigger context, I have stolen this picture from Luca's paper, which I like very much. And I also like this picture. So this nicely encapsulates the effort of Homo sapiens to understand the CFT spectra. And so I will briefly spend some time to explain this picture. So the point is CFT has a very rich spectra in the asymptotic limit. So we try to understand the CFT spectra and constrain it by various approach. So of course, the CFT spectra is parameterized by two quantities, scaling dimension delta and spin j. And often we have some extra symmetry like U1 or anything. So there is some extra handle, which is Q. So normally whenever people do bootstrap numerics, they basically look at this origin and constrain the spectra. Then you have this light cone bootstrap where basically you constrain the spectra near delta equals j, near the unitary limit. And then you have these all Cardy-like statements where you are looking at order 1 spin, order 1 chart, but you are looking at asymptotically large delta. And then there are these spatial states where you have this extra handle Q and you are looking at some large charge sector and the ground state of the large charge sector and the excitations above it. So, and this curve goes like Q to the power some d over d minus 1. And there are excitations here. And so whatever I am going to tell you is roughly speaking is applicable to this region. And we are not really explicitly assuming that there has to be some extra internal symmetry for our boost symmetry breaking. But we do assume something that in some sense that the state delta omega I am talking about is ground state of some modified Hamiltonian. So in our analysis, we are kind of agnostic about what this extra handle is, but roughly speaking, there is some extra handle. And you will see later by exactly how this assumption appears in our calculation. So basically we are constraining the spectra over delta omega, right? So we are assuming whatever appears in those correlators, all those states has scaling dimension over delta omega. So there is nothing below. So there is a sense in which the word excitation makes sense. So in that sense, we are basically probing this kind of regime. Okay. So now let us proceed and dive deep into the details. So let us start with the Goldstone theorem. So we'll have to write down the Goldstone theorems in a more useful form so that we can utilize it. So this is mostly done in this paper by Nicolis and Albertre, and we just wrote it down in a form which is useful for our purpose. So here, what is the first? So first of all, we take a state omega, which has a finite energy density. And because we are in a CFT, the finite energy density epsilon means you also have a finite pressure P. So this is energy density, this is pressure. And the fact that the boost symmetry is broken is encapsulated in this equation, where this is the boost generator, this is the order parameter O, and you can calculate this commutator by the algebra, and then you can see that this is related to epsilon plus P delta Ij. And because you are taking finite energy density, this is basically not equals 0, and you have a breaking. And on the other hand, you can take this generator Ki, and of course, Ki is related to, as I said, you T0i and T00. So basically, you can also rewrite this equation in terms of an integral of this commutator. So this tells you that this integral of this commutator is related to this quantity in this way. And so this is an integral from, and you can easily see that in the momentum space, this becomes simplified because this integral goes away, and then xi becomes a derivative in the momentum. So you can write down a momentum space version, which basically tells you that this commutator, the Fourier transform of the commutator, the derivative of that, if you take a soft limit, which is k going to 0, has to contain a delta function, and the proportionality constant would be related to this epsilon plus P. So this is a sort of sum rule we will be looking at, and we will see what kind of constraint it puts on the spectrum. So one more comment, often we strip off this factor of 2 twice pi and write down something called spectral density. So this is the form we used in our paper. Basically, it's the same equation, just stripped off factor of 2 twice pi. And suppose you have extra U1 or some extra current, then you can write down a similar kind of sum rule where instead of rho T00, you have rho T00JJ, where this is this extra current. And again, you can write down this sum rule and see that whatever appears on the left-hand side is related to the charge density rho instead of epsilon plus P. You can write down more sum rules. For example, you can think of sum rules appearing from Lambo-Goldstone theorem for broken dilatation, which basically relates this spectral density for Ti0, T00, and Ti0, J0 with these quantities. And I should also mention one point, which also has been mentioned to us by Luca over an email, that some of the sum rules can actually be derived from the sum rules. So the point is this red one and this red one are related by the fact that you can contract the indices and use the fact that in a CFT, epsilon plus P is related to d epsilon. Epsilon plus P times d minus 1 is related to d epsilon. And also, if you take this equation and you can relate it to this equation, the blue one is related to blue one. If you use the conservation law and the contraction of indices. So all I'm trying to say that these are not really new constraints. So if you can show that these constraints are satisfied in a CFT, you will immediately show that these are also satisfied. But still, you can write down these equations. So to move ahead, so if you are lost in the details, just to tell you that what we are doing, so we are taking a finite energy density state omega, and then you have this commutator where suppose A is related to the generator, B is the order parameter, and on this side you have something universal like delta of omega times some quantity epsilon plus P and so on. And what we are trying to do, we are trying to look for states. So we insert complete set of states here in between B and A and B. And we want to look for states which saturate the sum rule and reproduce this right-hand side, this universal thing. So the point is that the fact we have something universal on this side means that there has to be something appearing here in between. And existence of such states in the infinite volume limit put constraints on the finite volume theory. So this is the basic idea, and we will explore this idea when we have a CFT. So this will become a 4-point correlator on a CFT, and this breaking is like looking at the 4-point correlator in the S channel expansion. Okay, so to move ahead, we will write down one more sum rule, which is actually useful for our purpose, which is the T0 sum rule. So here, so as we already have written down, that for a boost, we have this spectral density which relates T00, T0J, and basically the derivative of this quantity in the K going to 0 limit. Now the fact is T0J is related to T00 by conservation equation. So you can immediately start from this conservation law and write down another equation, which tells you that the spectral density for this T0 correlator in the Fourier space in the omega, as a function of omega and K, should behave like this in K going to 0 limit. So we'll try to see how, like, what constraint this equation have on our spectra. So basically we will be starting the correlator, which looks like this: omega T00 tau n1, T000 n2, and omega. So you can see here I have used the notation tau and n1. So this implies we actually will be starting the correlator on a finite volume theory and take the limit. To be more precise, just to put things on ground, we will be considering a CFT with R times SD minus 1, which I already mentioned again and again. We will pick a state with a finite energy density, and basically we'll take the infinite volume limit, which we call macroscopic limit, while we'll keep the energy density finite and fixed. And the idea is the infinite volume limit should satisfy the sum rules. The aim is to identify the states that are responsible for saturating the sum rules and in the infinite volume limit, and that should translate to something in the finite volume theory. So at the end of the day, long story told short, we'll be looking at this correlator where omega is finite energy density. So is the basic setup clear? Is there any question? So if not, let me move ahead and see how these things can be done. So to say it again, that we have this sum rule, we want to probe this sum rule, and for this we want to look at this correlator. In particular, it is S-channel decomposition. So we have to show two things, as I said earlier, that descendants don't play any role. So we'll be looking at this correlator in the S-channel, and we'll first show that the descendants drop out in the infinite volume limit. So the descendants don't matter. So we have direct access to primaries appearing in this S-channel, and then we will put the constraint on those primaries. So the fact that the descendants drop out in the infinite volume limit is basically boils down to some properties of conformal block. So ideally, we should be looking at some spinning conformal block because these are some spinning operators. But it turns out in the macroscopic limit, because we are looking at some particular kinematical limit, it is sufficient to look at scalar blocks. And you can, even in the scalar blocks, you can see that the descendants drop out in the infinite volume limit. And the similar argument holds for the spinning blocks in this scenario. So in next, what I'm going to show you that how in the scalar blocks, these descendants drop out in the infinite volume limit. So just to recall, how do these blocks look like? So roughly speaking, the blocks looks like following. So you have a sum over m and n, which are some level of descendants. Then you have some coefficients, which basically are a function of the kinematical variable z, z bar, the cross ratios, and the OP coefficients. And you have some Gegenbauer polynomial. And this Gegenbauer polynomial depends on three numbers, which is L, M, and N. M and N, as I said, are the descendant levels, and this L is the spin that is the spin of the intermediate thing that goes into this S channel. So basically, you basically have this thing, and whatever appears here, this has a dimension delta and spin L. So this L appears in this quantity. So whenever we say them in the macroscopic limit, the descendant dropouts, what we mean that if you take the macroscopic limit, this sum is completely dominated by mn n equals 0 term. So now our job is to show this thing explicitly. So before doing that, so let us think what kind of blocks do we know. So for example, in 4D CFT, we do know these blocks explicitly, for example, the scalar blocks. So to be more explicit, we can write down these blocks in the following form, which is these are the blocks. As I said, these are a bunch of coefficients. This is the cross ratio function, and this is the Gegenbauer polynomial. So I will not give you the most general argument, but just to convince you, let us think about the 4D CFT. So in 4D CFT, what happens that this left-hand side, these blocks are explicitly known. These are some hypergeometric function, 2f1, you can write down, and people have written down differential equations, solved it, and found this thing. Basically, it started from this paper by Dolan and Osborne. So because you know this thing, you can actually take the macroscopic limit, which is basically the limit where you take the cross, you write down the cross ratio as 1 plus u over r. You take r to be very large so that u is fixed. So this u becomes your macroscopic coordinate. So what happens that if you have this block here, you can write down this block explicitly as a function of z and z bar, and then you can take this limit for various delta and L. And you can ask that if I take this limit on the left-hand side, on the right-hand side, what kind of summands remain, and what kind of summands on the right-hand side actually produces this limit on the left-hand side. So you can do this exercise explicitly by writing down the hypergeometric things, and you can explicitly see that only m equals n equals 0 term remains on the right-hand side to reproduce the limit, the macroscopic limit of the block on the left-hand side. So here delta and L can be order 1 numbers, or it can be as large as order r when you take this limit. And if you want to show this beyond 4D, then basically you have to learn about this behavior of this coefficient Rmn explicitly. But that can also be done because Dolan and Osborne has already found some recurrence relation for this coefficient Rmn. So you can just dig out all those results from this Dolan and Osborne paper and plug it into Mathematica and check that this thing works. And as I said before, there's this argument I just showed you is for scalar blocks, but even for the spinning blocks for T0, T0, the same argument holds. So,
question.
Yeah.
Is there an intuitive way of understanding it? I mean, I understand. You do the calculation, you see that it comes out like that, but why?
Let's see. Some intuitive way.
I mean, yeah, the Gegenbauer part clearly plays no role because it's just telling how it turns. So who cares? Everything is in the coefficients. But
yeah, I guess the point is that these coefficients gets suppressed very much. Yeah, I am not very sure. Like, yeah, on top of my head, I don't have any like physical argument. Because you also have seen, like when initially when I was talking about a more general argument, the more general argument was for all the operators. So yeah, yeah.
I mean, I'm just saying it seems to be something so general that maybe there is a simple, something that I can understand.
Yeah.
Oh, yeah, that's okay. Go on.
Yeah. Okay, so at the end of the day, we learned that that all the descendant contributions are suppressed. So because the descendant contributions are suppressed, we can move on and deal with primaries. So now we have only primaries in the game, and we want to see how this sum rule is satisfied. So first of all, this is a sum rule at infinite volume limit, and you have this variable omega and k. So this immediately tells you that somehow you have to, so this thing is related to the Fourier transform of T0, T0 correlator. On the other hand, if you write down the correlator on the cylinder, then basically is related to these Gegenbauer polynomials and this variable delta and L. So roughly speaking, that this expansion is basically you expand in the S channel. This is the contribution coming from the state omega and all its descendants. And then this is a new primaries that contribute to this correlator. And all these, and there are other contributions which are suppressed in delta omega. So if you take delta omega going to infinity limit, so this drops out. And the main player in the game is this quantity, which survives if you take the commutator. But the point is that here we will have Gegenbauer polynomials, and you have this delta and L. So first of all, you have to take the macroscopic limit of this quantity, somehow relate the Gegenbauer polynomial with the Fourier transformation, and relate this variable delta and L with omega and k, which is the macroscopic variable. So these are three things, these are two things we have in our mind, so we have to do this procedure. But it turns out, but naively what is being done. So you are looking at a very small patch. So on the sphere, you have this angular momentum modes, you are looking at a very small patch. And on that small patch, the angular momentum essentially behaves like angular momentum modes essentially behave like some plane waves. So there has to be some identity which relates this Gegenbauer polynomial with plane waves like e power ipx, and that's how we will relate it to the Fourier transform. So it turns out indeed there is some identity like that, which is this spatial identity. And this identity might look very complicated, but what it says that in macroscopic limit, the Gegenbauer becomes some angular average of plane waves. So basically, we are looking at a very small patch of the sphere when we take this infinite volume limit. And in this infinite volume limit, it looks flat. So you can write, so this is the physical content of this equation. And to go to the macroscopic limit, we have these variables omega and k. We can immediately go from delta and L to omega and k by introducing this delta function and by the scaling of R. So roughly speaking, this also depends on R, but one of the crucial assumption is when we take the macroscopic limit, like this quantity with the OP coefficient should have a very smooth R independent limit. So basically we take these two equations and we plug this into this equation. And once we do this whole procedure, the dust settles, and we can write down this nice macroscopic form of this T0 correlator. So where we have this epsilon square, and then you have this quantity capital K, which basically has all the data of OP coefficient of your new primaries, and this density of states rho as a function of omega and k. And you can see that the Gegenbauer becomes Fourier transformation. So this is e power ikx. And there was a power, and you can see there was a power of e power L tau over R, or delta tau over R, which basically becomes e power minus omega tau. So if you rotate it to the Lorentzian signature, this precisely becomes the Fourier transformation we want. So, and then we can basically read off the T0 correlator in the momentum space. So that's what we do next. We start with this correlator and read off the spectral density, which is basically related to this function k. To be precise, this quantity. So this p is related. This p and k are same. Sorry for doing this. Yeah. So for whenever I write p and k, they are same. So this spectral density is related to this k omega k. And now you have to compare this with your original sum rule, which tells that there is some particular behavior in the p going to 0 limit. And in particular, it has some delta prime of omega. So this tells you that this function k omega p, this quantity, must have some support on omega equals 0 and p equals 0. And this fact that it has some support on omega equals 0 and p equals 0, because you are taking p going to 0 limit, these two things immediately boils down to having these two equations here, which is delta gap over R goes to 0 and little l over R goes to 0. And so, And then you can recall that you can exchange R with the delta omega because your delta omega has some scaling with respect to R. So you can replace this R with delta omega, and then you have a bound or relation, which is completely a CFT relation, which tells you that delta omega or delta gap over delta omega to the power 1 over d goes to 0, and the spin over delta omega to the power 1 over d goes to 0. So this quantity is like R here, and this quantity is like R here. But so what does this tell you? So this tells you that you have excitation over delta omega, and these excitations has to satisfy this, these two equations here and here. And this tells you that the gap is of little o of R, so which is not quite order 1, as I said before. So I earlier said I would argue for gamma equals 1, but this is not quite gamma equals 1. This what it says that for every positive number, positive real number C, there exists a state which is below C times R, and this happens for every C. But this is not same as saying that the gap is big O of 1. So there's a difference between little o and big O, as you all know. So to argue for big O of 1 gap, one needs to further assume existence of some scale invariant theory which describes this infinite volume physics. So if you assume that existence of some scale invariant physics, then you can further restrict this equation, and you can say that indeed delta gap is order 1. And not only that, not only you can bound the gap by using these kind of rules, you can also bound the OP coefficient. Because you can recall that there is a quantity T00, T00, and in the macroscopic limit, it is related to something we call K omega K, which has a support on omega equals 0 and K equals 0. And this quantity is basically related to the density of states and the OP coefficients. So the very fact that this has a macroscopic limit means that in the R going to infinity limit, this cannot grow arbitrarily. So that means this quantity has to be bounded as we take the infinite volume limit. And this immediately tells you that this OP coefficients has to satisfy this bound. So it has to be of the order delta omega times R cube. So you have three equations from the CFT side. One is the bound on the scaling dimension, the bound on the spin, and the bound on the OP coefficient that for the states which saturates this sum rule, which cannot be larger than delta omega times R cube.
To assume that there was a scale invariant description, what exactly do you mean by that? Because there's finite energy density.
I mean, there isn't some EFT-like statement where you have write down some scale invariant Lagrangian, for example, in the superfluid.
But a Fermi liquid would satisfy that condition?
That's a good question. I mean, yeah, we do not know any of. Yeah, so for the Fermi liquid, the bounds are satisfied. You can at least for a free fermions, if you look at particle hole excitations and look at gaps over the thing, there is an order 1 gap, and they satisfy these kind of statements. Yeah, but then we do not know of any EFT for those kind part, like these particle hole excitations, for at least no local EFT. So yeah, for a free fermion, like at least for a Fermi liquid, it's not very clear, like whether one can write down some EFT.
Okay, but I didn't completely understand the kind of technical step in going from little o of R to O of 1. How scaling helped you do that?
Oh, so here, I guess the argument is that, you can think of for example, you can think of a superfluid EFT, for example. So there you have some superfluid EFT, there is some phonon excitations, and because you have phonon excitations, you can always excite 1 unit of something, and there is a Regge trajectory. So those kind of arguments immediately tell you there has to be some state with order 1. Yeah.
Right.
So roughly when we're going from this step to this step, is like what we have in mind is some superfluid like EFT. Like there is some EFT which describes things. So this step is really a physical argument, not some rigorous mathematical step we are doing.
Mhm. Right, right,
So
right.
from the CFT, all you can do, you can say it's little o of R.
Mhm. Okay.
Okay, good. And then, okay, I guess I'm running a bit short of time. So in the rest of my talk, what I'm going to do that, so we have these bounds like this, and this. So in our paper, we have verified these bounds in various setups. So in particular, we looked at superfluids, free scalar field in t greater than 2, in the free fermions, and in 2D CFT. And so basically in all these setups, we looked at this correlator and looked at the S channel and asked what are the states which contributes to this correlator in the macroscopic limit and responsible for saturation. So roughly speaking, this is what happens in a superfluid in the infinite volume limit. You have this single particle states, which is basically the excitations of Goldstone bosons. And on the finite volume theory, this becomes a Regge trajectory, as you all know. And they saturate the sum rule. And then you can verify that these rules are satisfied. You can do the same thing for a free scalar field. And for the free scalar field, basically you have like particle hole states. If you take a finite energy density state, over that finite energy density state, you have particle and holes. But effectively, these are different from the particle hole states of a Fermi liquid because they are effectively described by a single parameter. So effectively, they behave like a single particle state in the infinite volume limit. So again, you can think of this as a contribution from a single Regge trajectory. For a free fermions, things are a bit complicated in the finite volume case, but still you can show that there are particle hole pairs around the Fermi surface. And these particle hole pairs are actual particle hole pairs in the sense that they are labeled by 2 parameters, unlike this free scalar field, and they saturate the sum rule. And then you have 2D CFT. And as I said earlier, there is no Coleman's theorem. So you can break boost. And here you can see that, again, it's much like superfluid. So here you can see that there are single particle states. And these are new SL2R primaries, but in the 2D, you have a bigger group, which is Virasoro. So the things that saturate the sum rule are Virasoro descendants, but they are new SL2R primaries. And they also form a Regge trajectory, much like the superfluid case. And also you can verify the sum rules for hydrodynamics. So for the sake of time—
Sorry to interrupt again. I just have a quick question. So in 2D CFT, you had already proved something stronger, no? That the bound had to be, the gap has to be smaller than 1.
Oh, I mean, in 2D, the gap is kind of meaningless in some sense because, not meaningless, I mean trivial in the sense, because you are looking at this correlator here, and then this correlator is completely determined by the identity module. And you have the stress energy tensor and everything in the identity module. So you know what appears there.
Right.
So, yeah.
But I think, didn't you show that even if you look at only Virasoro primaries, the gap is, the gap has to be smaller than 1 or equal to 1?
Oh, but those are for those. Are you talking about the Tauberian theory things?
Right, yeah.
Oh, I see. Oh, but they are the, I
Okay,
guess.
so that was for SL2R primaries.
No. Those are also for Virasoro primaries.
Okay.
But the point is there, the statement is stronger, as you said, that they are Virasoro primaries and these are SL2R primaries. So that's one thing. And another thing is that there we are looking at a order 1 spin and delta going to infinity regime. So those are like Tauberian regime.
Right.
So
it's a different regime, I guess.
Yeah, so I guess I can again refer to your picture, which I like very much. So where is the picture? So the bound we proved is for this regime here, the Virasoro primaries. And the bound here we are referring to is in this regime. So they're slightly different regime.
Okay, thanks.
Okay. Where? Okay, yeah. Okay, so I will try to quickly go through the superfluid and the 2D CFT example. I should be very quick. So here we all know about superfluid things because it's a large charge community. So So roughly speaking, we consider a CFT on a cylinder with U1, we consider a state with large Q. And when Q is large, there is a UV scale, which is determined by this quantity, and there is a IR scale, which is R. And if Q is very large, then there is a separation of scale, and you can write down an EFT with 1 over Q being the cutoff. And this state breaks the symmetry U1 and also breaks the boost. So this is the symmetry breaking pattern. And because there is a symmetry breaking pattern, you can write down an EFT in the CCGW way. And this the EFT is the EFT of some phase field chi. So this phase field chi has some symmetry breaking vacuum wave, which is mu. And there is expansion, the fluctuation pi, which is like the Goldstone boson. So you can write down an effective action for this Goldstone boson, which is given by this. And this is basically the leading order superfluid action. And you know all these excitations are basically the Goldstone modes of pi. And again, I have stolen another picture from Lucas and Gabriel's paper because I like these pictures. So here again, you have delta and Q, and this roughly explains how the excitations are. So here you have like, so this should be D minus 1 over D over D minus 1 in our notion. But anyway, and there are these excitations which goes like square root L times L plus D minus 2. And these are basically the phonon excitations. So basically you can look at this correlator and ask what kind of state saturate this thing, and you can show that these phonons form a Regge trajectory, and this Regge trajectory in the infinite volume limit becomes single particle states, which are the phonon excitations, and they saturate the sample. You can show this very explicitly because you have an EFT description, so you can write down the correlator explicitly in the S channel, and you can read off the OP coefficients, which is given by this nice looking formula. And once you have the OP coefficients, you can basically figure out this quantity K I was telling you before, and from that you can read off the spectral density, which has a very nice and neat formula in terms of delta function. And now if you take the soft limit, which is P going to 0, you can immediately see that the sum rule is satisfied. And so this is the sum rule for T00, T00. If you take other quantities like other sum rules, all the other sum rules you can explicitly verify by, so if you want to verify the other sum rules, you take the appropriate correlator, write down the EFT contributions and read off the OP coefficients, and you can verify the sum rules. And you can do the same thing. Okay, so now comes Masaka's question. So what happens in the parity vibrating cell? So recently, Gabriel, Luca, and Umang wrote down a nice paper where they saw these extra excitations, which scales as Q to the power 3/2. So these are softer modes, but what happens? So in their setup, they have spin equal, like the ground state has spin equals 0. They also have this phonon mode. So the phonon modes and the vortex mode, they coexist. But even in that setup, what happens, the OPE contribution coming from the phonons do not get modified. So there also the phonon modes already saturate the sum rule. And this immediately tells you that there are softer modes. These softer modes, they cannot play any role in the sum rules. And this is in fact corroborated with the fact that, like, if you calculate the OP coefficients between these new states with the T mu nu or J mu, you will see that they are parametrically suppressed compared to the phonon modes. And there is another argument you can say that these are inherently related to the vortex solutions, and the vortex solutions can only survive in the finite volume. If we take the infinite volume limit, the vortex cannot survive. So the vortex cannot play any role in these sum rules. So the reason I put up this slide is following that. So just from knowing our sum rules, we can say that if there are other modes, so if there are other modes which coexist with phonons, either you have to modify the OP coefficients of the phonons, and if the OP coefficients of the phonons do not get modified in this new setup, then these other modes cannot play any role in the sum rules. Their OP coefficients has to be suppressed, or something has to happen so that they do not play any role in the infinite volume limit. So this falls out naturally from our analysis, and you can see this explicitly in their paper, which is very nice. Finally, I should wrap up with saying something about a 2D CFT. So in 2D CFT, of course, U1 cannot be spontaneously broken because so there's a Coleman theorem. So U1 is in a lock phase. But nonetheless, you can consider heavy states and boost can be broken. So you can consider this kind of correlator. And as I was mentioning, this is completely determined by the Virasoro identity module. So you have this quantity here, which you can write down very explicitly. So this is the full answer. And then you can take the macroscopic limit and ask what kind of states saturate the sum rule and what is the spectral density corresponding to this macroscopic limit. And one can see that the spectral density is explicitly given by this quantity. And if you take k going to 0 limit, you see this leading piece, which leading piece saturates the sum rule. And if you go through the analysis more carefully, you will see that, again, there are single particle states, which are like Regge trajectories, which saturate the sum rule. In that sense, this is very much like superfluid EFT. And these Regge trajectories are actually new SL2R primaries, but they are Virasoro descendants. So from that aspect, the story is trivial here because they are Virasoro descendants, but there is some uncanny similarity with the superfluid EFT. So that's why we have checked it. And finally, by this time, so we know in the 2D CFTs, the sum rule is saturated. So by this time, I have said a couple of times that it looks like superfluid EFT. So a natural question is whether you can write down an EFT. So in the last few minutes, I will switch gear a little bit and discuss whether we can actually write down some EFT which mimics the superfluid EFT and reproduce this correlator in the infinite volume limit. So we can write down an candidate EFT, which would be the superfluid EFT specialized to D equals 2. So again, you can write down a field phi, which looks like the chi field. And then you have this quantity here, which is the leading order behavior. And then you have to add some correction terms so that if you do an EFT computation with this Lagrangian, you will reproduce this correlator. And it turns out you can write down this kind of terms, which the story resembles very much like EFT of long string by Polchinski and Strominger. And once you write down this Lagrangian, you can use this EFT to predict some stuff. For example, one prediction of the EFT is that if you take a large star state which breaks the boost, then the delta Q has to scale like Q square over twice kappa plus C minus 1 over 12. So the analogous equation in superfluid EFT is delta Q goes like Q to the power T over D minus 1. So this is the analogous statement here. So once you have prediction for if from the EFT, you can also ask whether you can push this EFT further up and write down something more general, whether you can push it to higher order. So it turns out that you can do it. The crucial observation is that all the EFT terms that you can write down, all of them vanish on sale. So you can do a field redefinition, which makes the EFT Lagrangian in this free field form. But note, even if the Lagrangian in terms of this redefined field phi tilde looks like a free field, the stress energy tensor is not the usual free field one. It cannot be because when you do the field redefinition, the stress energy tensor also gets corrected from this redefinition. And so effectively it boils, so if you want to write down a higher order thing, effectively it boils down to following question, that whether you can write down a general form of stress energy tensor with this field phi tilde and impose TTOP for arbitrary central charge. And so you can try to do it parametrically, order by order. And it turns out that if you only focus on the stress energy tensor, you can do it to arbitrary order with arbitrary central charge C. So I have not written down the full expression for, you can do it. But there is some immediate problem if you also try to impose something else what we know about 2D CFT. So we know that if we have a discrete spectrum, then any U1 symmetry in a 2D CFT should be promoted to the Kac-Mood U1. So there is a left moving U1 and a right moving U1, and it's going to get promoted to the Cock mode U1. So if your state omega is not only a Virasoro primary, rather a Cock mode primary, then you also have to impose JJOP and TJOP. So earlier I just told you I imposed the TTOP with arbitrary central charge. But then if you want to do the same argument by doing the input, if you try to impose the JJ or TJOP, you are forced to have C equals 1. And then it boils down to some paper by Affleck long back where he actually argued for the scenario that if you have a free boson, like if you have a theory which you can only build by a single scalar field phi tilde, then there is no, and if you have Cock mode, then there is no way out. You are forced to have C equals 1. So we basically explicitly see it by trying to construct these operators. So this means in our setup, either we have to give up on Cock mode symmetry, which means such CFTs cannot have discrete spectra, it must have continuous spectra. So that something weird has to happen, or we are forced to make C equals 1, in which case the EFT story is trivial, not that exciting. But still we have written it up because a more interesting, so the setup could be more interesting for perhaps for large charge sector of some boundary 3D CFT, where one needs to take into account of the boundary trace anomaly. And then this extra term, which I wrote down here, which is like the central charge here, this could play a role to take into account for this boundary trace anomaly. So in that sense, this EFT might be useful. So with that, I will stop here and thank you.
Okay, we already had a couple of questions, but are there more comments?
I had a question. Oh no, yeah, go ahead.
Go, Luca.
Okay, great. So this EFT thing, 2D CFT EFT thing is kind of reminiscent of Liouville theory, how Liouville theory in the thermal case in a large dimension can kind of reproduce thermal correlation functions semi-classically. Have you thought a bit about?
No, I haven't thought about it. Can you tell me more a little bit?
Sorry?
I haven't thought about it. Can you tell me a little?
Well, I mean, I'm not an expert on this, but it's kind of you can you know, reproduce the Cardi formula kind of semi-classically in Liouville theory, kind of in a similar way to what you're doing at large charge.
I see.
And it's like a, you know, to leading order a free scalar field as well. I don't know. It seems a little similar.
Yeah, it might be related. So I guess to begin with, we are very excited about this EFT because we wrote down first few terms and it was working well, and then basically Mark wanted to code it up and try to go to 7th order or 6th order. And then at 6th order, we are forced with this inevitable thing that C equals 1. And then we found out the paper by Affleck that there is a theorem. So we should have guessed it to begin with, but anyway. So we learned it hard way.
But why is it a catastrophe that it's a continuous spectrum, since it's an effective theory?
Say that again.
I mean, why is it a problem for the effective theory to have a continuous spectrum?
Oh, it's
On
not.
this theory.
I mean, yeah. So normally when we're talking about CFTs on a finite volume, we normally think about a discrete spectrum because we are in a compact volume and so on. So in that sense, CFTs with continuous spectra is in some sense weird, but you can always say, like, we have examples like Louisville where you have continuous spectra. Right. So yeah.
I mean, it's an effective theory. It's not the. It's not supposed to be the. You know, the real thing. Like, as long as it works in the interval of energies where it should work, you're okay. No.
But that's the point. I mean, it doesn't.
It doesn't.
I mean, there's no just in the interval of energies where it should work. There should be a discrete spectrum.
Yeah.
Not a continuous spectrum.
So this continuous
discrete versus continuous spectrum and finite volume isn't a low energy issue versus microscopic issue at all.
Yeah, yeah. Yes.
Okay. But so what about that prediction that you had before, that the conformal dimension go like q square plus c minus 1 over 12. Okay, so for c equals 1, that's obviously q squared. That's fine. That's everything is fine. That's all. I mean,
boring but fine.
But be boring but fine.
Yeah,
But you can't have a prediction for other CFTs that have c different from 1 coming from here.
Yeah, not
Am I
for
under-
not for the case where you have a discrete spectra and U1 is promoted to the cup mode U1. Yeah, no.
Okay.
Yeah, that's true. But I guess, yeah, I guess I haven't really thought about this, but I think more interesting avenue to like use this EFT to do something else. Probably this like boundary 3D CFT where you have this trace anomaly and you can try to reproduce the boundary trace anomaly by these terms. So on. I think that would be a more like potential good avenue to explore this. And there, this kind of predictions will still hold. So one point is that if you do not have this issue of U1 Kakmodi thing, then this prediction is very robust in the sense that even if you go to higher order in Q, that there is no corrections. So in some sense, this is true in E power minus Q level of accuracy. And all this comes from the fact that effectively this Lagrangian has this form, that del phi tilde, del phi tilde. So modulo this issue of Kakmodi 1, this prediction is pretty robust. So if you can somehow bypass this issue of Kakmodi by thinking of other setups, then it could be useful.
So you referred to a theorem by Affleck, but I mean, in 2 dimensions, isn't there just doesn't the Sugawara theorem make it almost impossible to have?
Yeah, Affleck basically uses Sugawara theorem. Yeah.
I mean, I don't actually know how Affleck's thing is different from the Sugawara theorem, but
I think it's not really different. So basically the argument is you have a U1 and then you show that because it's a discrete spectra, there is a state operator correspondence, the U1 gets promoted to U1 times U1. And then basically you use Sugawara to say that it has to be Kakmodi. So that's the argument. Yeah. I
see.
get, yeah. Yeah, the Affleck came because we are looking at this Polchinski-Strominger thing where this extra U1 becomes the target stress momentum. And there Polchinski and Strominger says that this extra thing cannot be holomorphic because you have this theorem. And then he referred to Affleck. So we also referred to Affleck. Yeah.
I see.
Can I ask one question, Sridip?
Yeah.
So, yeah, good to see you again. So I'm a bit confused. So there are 2D CFTs with non-zero, sorry, like a center charge not equals to 1, but you can still consider the large charge sector, right? And
yeah, but I guess then the point is probably you cannot write down a EFT with a single.
Right. Yeah. So probably you need to look for something different. That's your prediction. Okay. I just wanted to confirm that.
Yeah. Exactly. Yeah. Yeah. So the point is this EFT wouldn't work, but maybe you can introduce more fields and bypass that. Yeah, that's true.
Any other questions?
Oh, yeah, I had one more actually. So going back to higher dimensions, you said an input necessary for your story is to have a Hamiltonian whose ground state.
I didn't really forgot to mention. Okay, so the assumption is following. So if you look at this thing in the S channel, whatever appears here has scaling dimension over delta omega. So like is basically Simeon pointed this out while I was giving the talk at IPMU. So that's the assumption. Like whatever appears in S channel has a scaling dimension over delta omega. So in that sense, delta omega is some ground state of something which we're agnostic about.
Right. So I guess my question is, can it apply to the large spin? Because there we know the gap to multi-twist operators, and it seems like you could make reasonable.
Yeah, I guess, yeah, that's a good point. Yeah. Yeah, I guess if you have a macroscopic limit and if you can think about this, some constraint, yeah, you can. Yeah, this could also be a potential avenue. I agree.